Okay. Okay, so let's, after our interlude in Ramsey theory, return to random objects. And I'm going to tell you about a very useful and powerful inequality due to Janssen. I'll give you at least one example, one application. So before I get on to the inequality, let's motivate a little bit. So you remember the Erdös-Rényi random graph GMP. And we answered the question, when does this contain a triangle? Okay. So we have a question. Given a graph H, when does GNP contain a copy of H with high probability? Is so this is asking, so given a function P of n, the question is the probability H is contained in GMP, does it converge to 1 when n goes to infinity? Right, supposed to write Q. Right. So, sorry? You can think of H as being a triangle, yeah. The question is general. But we answered it for the triangle. So we proved the probability that there exists a triangle in GMP converges to 0 or 1 if P is much smaller than 1 over n, or if P is much bigger than 1 over n. Okay. And in more generality, one can show the following. For not any H, for balanced H, I'll tell you what that is in a second. One can show that the probability there exists a copy of H in GMP goes to 0 if the expected number is small. What's the expected number? Well, it's just P. Okay, you tell me. What's the expected number of copies of H in GMP? Thank you. Times? The number. Yeah. Okay. Sorry? Yeah, the same as choose, right? Because, sorry, I don't mean G, I mean H. Sorry. So n choose the number of vertices and n to the power the number of vertices differ by a constant. Constant which depends on h.
More or less kind of e to the number of vertices or not? Because that inequality that the binomial is bigger than just the power. No.
Yeah, so it's between n divided by v of h to the power v of h, and at most e times the same thing, the power v of h.
Power
Yeah, so both of these things are approximately n to the power v of h, right? They're both n to the power v of h times a constant to the power v of h.
we're assuming that the number of vertices is much smaller than that.
Well, we're assuming it's constant. Sorry. So this is all for a small fixed subgraph h and n big. If you want to look at an h which varies with n, it's another question and it's a good question, but let's start simple. So, okay. So for small h and n tending to infinity, then you can prove there's a threshold at this value of p, right? So p is roughly n to the minus v of h divided by e of h. Sorry, that's very noisy.
Maybe the expected number of copies of h is can it be also the probability zero when the number of edges go to infinity?
Number of edges of h?
No, the number of copies, the expected number of copies of h
Ah.
goes to infinity.
Uh-huh.
The probability is
Yes. So this can happen.
cannot happen.
It can happen. Yeah. This theorem says when h is balanced, it can't happen. I haven't said what balanced is. But here's an example where it does happen. If h is a triangle plus an edge, then what is the expected number of copies of h? Well, it's p to the 4. It's got the same threshold. Okay, let me do a better one. This is better. Okay. P to the 7 times n to the 5. Okay? So this goes to infinity if p is much bigger than n to the minus 5 over 7. Okay? But, fact, K4 is balanced. Okay. Well, we don't even need this fact. It's just we use Markov. So what's the expected? Yeah. Sorry, let me not use facts I'm not telling you. This is okay. What's the expected number of K4s? Well, p to the 6 times n to the 4. And this converges to 0 if p is roughly n to the minus 5 over 7. Well, even if n is as big as n to the minus 2 over 3. Right? Note that 2 over 3 is smaller than 5 over 7. Right? So there are functions p much smaller than n to the 2/3 and much bigger than n to the 5/7. Yeah, because they're minus, yeah. Is it okay? But if the expected number of K4s goes to 0, well, by Markov, the probability there exists K4 is at most the expected number, so that also goes to 0. So here's an example for any function in between these two functions. Certainly, if there's no K4, there's no K4 plus an edge. Right? So the probability that exists a copy of H goes to 0, but the expected number goes to infinity. Yeah. So this can absolutely happen. So perhaps this gives you a hint of what balanced means. H is balanced if there doesn't exist a denser subgraph. Okay? So it's balanced if the number of edges of F divided by the number of vertices of F is at most the edges of H divided by the number of vertices of H for all F subgraph of H. I guess non-empty. Otherwise, this doesn't make sense. Okay. So a recap. We're in GMP. We're asking whether GMP contains a copy of a fixed graph H. Okay? Is it okay? Yeah? Sorry, if you look blank, then you have to give me affirmation that it's making sense. Then I claim there's a threshold at this value of this function p. What does that mean? It means if p is much bigger than this function, then the expected number of copies of H goes to 1. And the theorem says, okay, so let me go more slowly. If p is much smaller than this function, that means that this is the expected number of copies of H, p to the e of H times n to the v of H. Then that goes to 0. Therefore, by Markov, with high probability, there's no copy of H in GMP. Is that okay? So it's just this. The probability there exists a copy of H is at most the expected number of copies of H. This is Markov.
Why H?
H is an arbitrary graph that's balanced, where balanced means this. Okay? But actually, sorry, for this part, it's an arbitrary graph. For what I said so far, works for any H. Okay? So if the expected number of copies goes to 0, by Markov, with high probability, the number is equal to 0. Okay? That's just this inequality we've used lots of times. Probability that something, there's at least one, is at most the expected number.
What is K4?
So K4 was what I needed for this other example, but it could be anything. Yeah. So this is any H the same h. So the theorem says that if h is balanced, then in fact this is the correct threshold. So this simple argument using Markov gives the correct answer, that if p is much bigger than this, then you're very likely to have a copy of h. This is the point at which copies of h appear. But it's only true if h is balanced, which means that there's no denser subgraph of h. If h has a subgraph which is strictly denser, meaning number of edges divided by number of vertices is bigger, like in this case, then the threshold is different. Can you guess what it is? What should the threshold be in general? What should it be determined by?
The lower bound you can have, I can use the most dense subgraph.
Yeah, you take the densest subgraph and so it's n to the minus, it's called 1 over m of h, or minus m of h, where m of h is the max e of f over v of f, such that f is contained in h. Okay. So I'm not going to prove either of these theorems. We already proved the one for the triangle. This one, the same argument works if h is strictly balanced, which means that you have strict inequality here. But it's already tricky for balanced. The proof in general is a result of BOLLOBÁS from the 80s. It's not so hard, but it's non-trivial. It's highly non-trivial. You basically look for the densest. So you find your densest subgraph. You find one of those. Then you have to extend it to the next densest one, and so on and so on and so on. So you build up your copy of H step by step. Okay. So this tells you where the thresholds are. I want to ask a different question, which is, what happens when p is a constant divided by n? What happens between these two functions? So we know what happens when p times n tends to 0. We know what happens when p times n tends to infinity. What happens in between? Okay, so the question for today is, so let p be c over n for some constant c. What's the probability there's a triangle in GMP? Is it close to 0? Is it close to 1? Is it something in between? Okay. And the answer is not obvious. But maybe we can guess what the answer should be. So we're interested in the probability. Okay. So that's, as usual, let x equal the number of triangles in GMP. Okay. As always, I should have made you tell me this. If you want to know if something exists in a random object, you define a random variable saying how many are there. Okay? This is always the first step. Okay? And now let's study this random variable. Okay, so what is the probability that x equals 0? Okay? The probability that there's no triangle in GMP. Roughly. So, yeah, so I think you're using a so that's the expected number of them, right? So the expected value of x is what? Say it again? So it's the number of triangles. So this one is easy, just the expected number. Forget C, just tell me with about P and N. Thank you. Yeah? Exactly this. Right? This many potential triangles, each one has probability P cubed. And this one is roughly, okay, now we can do it. This is roughly P cubed N cubed over 6. So it's like C cubed over 6. Okay? So there's some constant expected number of triangles. Right? Okay. But I want to know about the probability that it's 0. So if you wanted to know if there's a triangle or not, one thing you might do is go through the triangles one by one and say, there's a triangle in the complete graph. Is it in GMP? Yes or no? No, it's not. Okay, there's another triangle. Is it in? No, it's not. There's another one. No, it's not. And so on and so on and so on. Each time, what's your probability of having the answer no? So every time I look at a triangle, it has probability P cubed of being in if you didn't know anything. So 1 minus P cubed of not being in. Right? This is, I think, what you were trying to say. And, okay, so it's not exactly 1 minus P cubed after you've asked a few times, right? Once you've heard the answer no a lot of times, start to get a bit disheartened, maybe it's less likely you'll get a yes next time. But it's only slightly less likely, right? Even if you've heard no really a lot of times, you're probably going to hear no anyway. You're only expecting to see a constant number in total, so it hasn't changed your distribution very much. Right? Has a little bit, but not too much. So this thing should be roughly 1 minus P cubed almost till the end. So it should be roughly 1 minus P cubed to the power n choose 3. Okay? There's no proof here. This is just an intuition. Okay? And you're definitely allowed to disagree with the intuition, even though it turns out to be right in this case. Why it should be true? So I haven't really told you yet, I guess. But if you believe, so you understand you're going through the triangles one by one, and you just go through until you find one. And the first one you look at, your probability of finding it is p cubed. Right? You don't know anything, the first one's p cubed. The second one, well, if it's disjoint from the first one, it's still p cubed. So you carry on. Eventually you get to a triangle intersected one already, then your probability is a little lower, but not so much lower. Right? All you knew is that it wasn't a whole triangle, which doesn't tell you very much about any one edge on it.
Is this very lower or maybe higher?
No, because you heard the answer no. Because you, as soon as you hear the answer yes, you can stop. Yeah. Yeah. So your probability's gone down a little bit each time, but hopefully not by much. But what have we proved? Exactly because of what you said. Yeah, at each step, the probability of seeing a triangle was a little lower. So the probability of not seeing a triangle was a little higher. So we've proved that the probability that you never see a triangle is at least what you would get if every question was independent. Okay? Okay. So there's a more general version of this statement. So this is known as the FKG inequality, not for triangles in more generality. In fact, it was first proved by Harris, and then by Kleitman in more generality, and then FKG in more generality, and then by some other people in even more generality. But anyway, for some reason, their name stuck. Anyway, so here's what the equality is. So what is the FKG inequality? It says the following. So we want to compare, given two events, the probability of A and B with the probability of A times the probability of B. Okay. If A and B were independent, we would have equality. Okay. We're interested in when we have inequality. When can you say the probability of A and B is more likely than the probability of A times the probability of B? When they're independent, they're equal. You have equality here. So certainly in that case. Yeah. But more generally, so if A and B, suppose we're just dealing with random graphs. So there are events that depend on the random graph that you see. So suppose they're both increasing in the sense that if you add more edges, they become more likely. Then they should be positively correlated. Right? This is saying that A and B are positively correlated. And FKG says this is true if A and B are both increasing. So, what does increasing mean? So A is an event, which means, let's say it's a subset of 0, 1 to the n. Or equivalently, A is a subset of or the family of graphs with n vertices. Okay. These two things are the same thing because by setting capital N equal to little n choose 2, then you can encode a graph as a 0-1 sequence. Okay? So these are just two completely equivalent formulations. This one is perhaps a little cleaner to think about. Okay? So A is increasing. Am I writing that correctly? Okay. If what? If a particular x being an A and x being at most y, these things are vectors, right? Implies that y is in A. Or I should put my line underneath. Right? So x and y are members of the cube. Or if you like, they're graphs. Right? So the same thing. Let me write it a little further to the left. X in A, x at most y. So this means coordinate-wise. Then every coordinate y is bigger than x. So, okay. Now I should write xi most yi for all I. This implies that y is in A. Or similarly, if G is in A and G is a subgraph of H, that implies that H is contained in A. Is it okay? You can think of this A as a property of graphs, if you like. That if G has the property and G is contained in H, then H also has the property. Okay? Is everyone happy? So this is a basic concept, and so it's quite important that you're comfortable with it. And this is a very, very usual thing in combinatorics to jump between these two slightly different setups without mentioning it. So I might do that a lot without thinking. If so, I apologize. Okay? Okay. So for any increasing property, for example, A could be the collection of graphs which contain a triangle. That's an increasing property because if you add edges, you don't destroy triangles. Right? Or similarly, if the property is the graphs which contain a particular triangle, that's also increasing property. Right?
They are both decreasing.
If they're both decreasing, it's also true. However, if one of them is increasing and the other one decreasing, then the inequality is the other way around. Then they're negatively correlated. And both those statements follow easily from this one. Just consider the complementary property. Is it okay?
What's the content of the FKG theory? If A and B are
Increasing,
then we have the
positive correlation.
positive.
Yeah, so probability of A and B is at least as big as probability of A times probability of B. This means they're positively correlated. So increasing events are positively correlated.
Give an example in this first.
So it could be A is the property that x1 equals x2 equals x3 equals 1. This is an increasing property that corresponds to this particular triangle is in the graph. Or these particular three edges, I should say. So maybe they form a triangle. So an increasing property doesn't have to be so simple. It could be, A could be the sum of the xi's is at least 7. Or it could be some combination of lots of these kind of statements.
But if y, I forget the name of the
Yeah.
y is bigger, I is bigger than x
Yep.
in the first,
Yep.
doesn't mean that
Yeah, so all of the xi's and yi's are just 0 or 1. So if x is in, that means x1 and x2 and x3 are 1.
okay,
And y is bigger, so y1 and y2 and y3 also have to be 1.
okay.
Yeah, it's just that. Okay? Okay. So how do we use this inequality to prove this statement? Well,
In this case, it's decreasing.
uh,
Having no triangles.
no, so I haven't said what the events are yet. So what should the events be?
No this triangle.
Exactly. Yes, so sorry, you're right, they're decreasing. Yeah. So we want to call the triangle T be the event that T is contained in, I guess T is not contained in GMP, for each triangle T. Okay? So for each triangle T, we define a random variable which is, we define an event, an event. Okay? And the event that x is 0 is equal to the intersection over all triangles T of AT. Right? And as I said, AT is decreasing. This implies, by FKG, probability that x is 0, which equals the probability of this intersection, is at least the product over all triangles T of the probability of AT. The probability of AT is just 1 minus p cubed. So it equals product over T, 1 minus p cubed, which equals 1 minus p cubed to the n choose 3. Okay? So that's just a very slow way of proving what you already believed way back here. But it gets you thinking about monotone events, increasing and decreasing events, which I think is important. And we're going to use these events again. Okay. So the aim will be to show that this inequality is close to being sharp. Okay. So our aim is what? So what have we proved? Well, remember that 1 minus x is at most e to the minus x, right? Well, that's not very good because we have a lower bound of the form 1 minus x or something. So we'd like to use a lower bound on this, which is e to the minus x squared. And this holds if x is small. Maybe it holds always. Anyway, it certainly holds when x is small. No, sorry, it can't hold always because 1 minus x will be negative. Sorry, yeah. Okay, so if x is close to 0, then this is true. Okay, so in that case, 1 minus p cubed to the power n choose 3 is at least e to the minus p cubed times n choose 3. Did I make it smaller? Yeah, it's smaller. And I guess I want... No, that's fine. Sorry. P to the 6 times n choose 3. Right? Just applying this inequality. But this guy is tiny, right? P to the 6 times n cubed. When p is constant over n, he basically doesn't matter. This term here. P to the 6 times n cubed is like 1 over n cubed. Okay? So this one is little o1. Okay? So this thing converges to e to the minus the expected value. Yeah, p to the 6 times n cubed for this value of p is roughly 1 over n cubed. Okay, which is tiny. Okay. So our lower bound converges to e to the minus the expected value of x, which is c cubed over 6. Okay. So this is a sort of important heuristic to bear in mind. If you have a bunch of events which are sort of independent, not completely independent, but sort of independent, then the probability none of them occur should be e to the minus the expected number of them. And that's what we're going to prove. So I can finally state the Janssen inequalities. Okay. So they're not going to be as general as FKG, so let me tell you the setup where they work. So what do we have? We have a sequence of M of sets, finite sets. Okay? And we have some p between 0 and 1, probability. and we have some S which is a p-random subset. That means you choose each element independently with probability p. Okay? So you should think of capital N as being little n choose 2, the edges of the complete graph. And this is a random graph. Right? Okay. Now, for each set, we're going to define an event. The event Bj is going to be the event that Aj is contained in S. Okay? So we have a random set S, and for each set, we have an event that says that set is contained in S.
These AGs are of size n.
They're no, any size you like. They're subsets of 1 up to capital N. This is, you should think of it as being the edge set. So this is like the edges of the complete graph. So we're taking subsets of the edges of the complete graph. Even better, think of each of these as a triangle. Right? There have each set, we have M is, you should think of as being little n choose 3. And each Aj corresponds to a particular triangle in the complete graph. Okay? And then this is the event that triangle is contained in GMP. Right? So it's the opposite of AT. It's the complement of AT. Okay? But this is the general setup. So any sets you like. Any sets of edges. Or any, if you like, you can think of these as being particular subgraphs. Is it okay? Okay. So we are interested in the probability. So theorem Janssen, 87 or something. So reasonably recently. Probability that none of the events Bj occur is what? Well, it's at least the product of the probability of the events. Okay, so it's going to give an upper bound. So let me give a general lower bound first. So just using the same method. So what do we know about the probability that none of the events Bj occur? Yeah, these events are all increasing. So these events are all decreasing. So by FKG, they're positively correlated. There's probably at least the product of the probability of Bj complement, which is the same as 1 minus probability of Bj. Sorry?
Bj complements decreasing.
Yeah, exactly. Yeah, so all of these events are decreasing. Yeah. Now? Okay.
Could you repeat why they are decreasing?
Because they're just of the form Aj is contained in S. So Bj is increasing. Because if you add extra elements to S, this becomes more likely to be true. So if Aj is contained in S, and then you add elements to S, Aj is still contained in S. So in that sense, they're increasing. Okay. So it doesn't become false when you add more elements in. And if bj is increasing, that means bj complement is decreasing. Right. Okay. Okay. So this is roughly equal to, by this argument, the product of e to the minus the probability of bj, which equals e to the minus the sum of the probability of bj over j. Right? Product of exponentials is exponential of the sum. And this sum over j of probability of bj is equal to mu, where mu is the expected number of bj which occur. So if we write x to be the number of bj validus, I don't know how to say this. Qui occurring? Okay. Cool. 1 hour or 2? Hang. Double. But 1c probably. Yes. Okay. Then, and mu is the expected value of x. Then this probability is not actually greater than, but more or less greater than e to the minus mu. Okay? So this is a more general version of what I was just saying here.
This inequality 1 minus x is holds for every x.
This one is for every x, and this one's only for x close to 0. Less than 1 over 10 or 1 over 100 or something. Okay? So, our lower bound is roughly e to the minus mu. Our upper bound is going to be, okay, there's 2 possibilities. It's the most e to the minus mu plus something called delta over 2. If delta is at most mu. And, okay, let me tell you what delta is before I tell you the other half. Delta is basically the variance.